So this paper is about deep learning and the pre-normalization of the neural network architecture. So in this paper, the authors propose using the recently introduced mini-batch normalization trick to evenly distribute data points across many linear regions defined by subnetworks in a deep learning network which rectify linear ReLU. Then they used mini-batch normalization units followed by max-out units to replace the ReLU units in the in-network model. So move to next slide. So this slide is a bit technical. So here I'm going to give a general introduction to the piecewise activation function. So rectify linear ReLU, which is the most used activation function these days, is one of the piecewise linear activation function. The ReLU function can be extended to leaky ReLU or parametric ReLU, which scales the negative input values of the unit by a scalar. The max-out recently is a much complicated piecewise linear unit. It competes several input activations and only output the maximum one. So that's the brief concept of batch normalization. So why normalization is quite important for piecewise piecewise activation function. The original paper, for the max out, says batch normalization regularizes the network. So here we think it is useful because that every input channel response is normalized to value range 0 to 1. Then effectively the number of points activated by this input channel is only halved. So which results into an even distribution. So it can be imagined as a straight line is drawn across the center of the point cloud. Then for each point, each input channel can compete with each other. So what about the result if we don't normalize them? So the activation function all points may be all positive or negative y. So the initialization of weights is always generated by some random values around mean equals to 0, which means the boundary hangs around the origin of the space. So the author has produced some results on a toy dataset. So that's the visualization of the piecewise rectified linear network on the synthetic dataset. So the first row contains ReLU and max-out network without using batch normalization. So for different symbols, so L represents the number of layers, so N refers to the number of units, and K is the number of linear pieces. It's for max-out only. So as you can see from the second row, so the results are with batch normalization, so they have much lower classification errors and much smaller and well-distributed regions. So in this slide, the author proposed a new network architecture. So this is a classification model we used in the experiment. The base structure is from network paper. So what we did was to replace the rectified linear in NIN by batch normalization max-out unit. So we ensure that the model has the same number of units per layer, same field size, pooling size, number of layers. So we did this merely to ensure a fair comparison in the different architecture. So the author's paper proposed method has reached state-of-the-art result in 3 different object recognition datasets, which is SVHN, CIFAR10, and CIFAR100. Looks quite well. Yeah, so if you have any further questions, feel free to come to the poster or write an email to the authors. Thanks.